This is the lesson I was hoping to go over with you today. 3.5 Limits at Infinity. This section discusses the end behavior of a function on an infinite interval. So we're going to first start out looking at the function f of x equals 3x squared over x squared plus 1. Remembering what we knew from pre-calculus, you might remember that if n is equal to m, if the degree of the numerator was equal to the degree of the denominator, then we have a horizontal asymptote at y equals their coefficients. So it was sort of like that. So if, I think this was supposed to be m and then n. So if these two degrees are the same, then the horizontal asymptote is at their leading coefficients, the ratio of their leading coefficients. So for us, these two are the same. There's that leading coefficient. So the horizontal asymptote is at 3 over 1, or 3. But let's look at the calculus behind it. Let me attach this picture. So here's the graph of it. We're looking at an infinite interval. So let's look from like this value here all the way to positive infinity. What's happening? Well, it seems to be leveling out, and it doesn't seem to be able to cross this horizontal asymptote at 3. But on a table, if you look at the table from 0 all the way out to positive infinity, and you just sample some x values, 1 is at 1.5, 10 is at 2.9. Wow, that's not a very large jump in y values for that many x values. Look at this big jump in x values, and we're still just at 2.9997. So we would say that that has a limiting behavior. It seems like the further the x gets toward infinity, the more the y value is leveling off at 3. 2.9, 2.99, 2.9999, 2.99999. So we would say it's approaching 3. And which would be an asymptote. That'd be an asymptotic behavior. It's approaching 3 value there. Same thing happens on the left. As your x values are changing and getting progressively larger, the y values are growing closer and closer to 3. So we say it's approaching 3. So here it is symbolically. I don't really think you need to write anything down yet. You might want to write this. The limit as x approaches, if the limit as x approaches negative infinity of a function is equal to a constant. And bye. See ya. 3 is that constant. 3 is our L, some number L. Then that would be an asymptote. And same thing as the limit as x approaches positive infinity of your function. If that value is 3, then that means there's a horizontal asymptote. So the line y equals L, y equals that number, and the other example is y equals 3, is a horizontal asymptote of the graph of f when the limit of the function as x approaches negative infinity is L, or the limit of the function as x approaches positive infinity is L. And then this next theorem This next theorem says if R is a positive rational number, it's any number that can be written as a ratio, like something over something, rational, and C is any real number, then the limit as x approaches infinity of C over x to the R is 0. Or if x is less than 0, if x is negative, the limit as x approaches negative infinity of C over x to the R is 0. So what they're saying is the limit as x approaches infinity of some number divided by x to some rational number, that's equal to 0. We had a little bit of this back when we did infinite limits. We had a regular number divided by a really huge number. This is infinity to the third power. And a regular number divided by a really huge number went to 0. So that's just this function written out a little bit differently. And we're going to use this definition here. Example 1. Find the limit as x approaches infinity of 5 minus 2 over x squared. Okay, so we're going to separate this out and do the limit of both parts. So this first part, there is no place to plug x in. The limit of a constant is just the constant minus. This next part, this is that C over x to the R. It says if the limit as x approaches infinity of C over x to the R, that's regular number 2 divided by infinity squared. That is going to go to 0. And 5 minus 0 is 5. So the line y equals 5 is a horizontal asymptote for this graph. If we went through all the math, got a common denominator, doing the butterfly thing, then we would see, oh, looky there, our degrees are the same. So our horizontal asymptote is at the ratio of the leading coefficients. 5 over 1 is 5. So pre-calculus agrees with calculus. Example 2. It should agree. The limit as x approaches infinity of 2x minus 1 over x plus 1. So what we're going to do here is we're going to have a strategy, because we're going to try to force that C over x to the R to, x to the R to come into play. So what we're going to do is we're going to find the highest degree of x in the denominator. And then we're going to divide every term by x to that degree. So this is one strategy. So when you look at the denominator, this is the only power of x in the denominator. So it's the highest degree, and it's a first degree. So what we're going to do is we're going to rewrite this. We're going to divide every single term by that x. It's the highest degree of x in the denominator. We're going to divide every single term by it. Now, some of these things are going to simplify. 2x over x is 2, minus, I'm going to leave that as 1 over x. X over x is 1, plus, I'm going to leave that as 1 over x. Now, we're ready to take the limit. When you plug in infinity, 2 is still going to be 2. But this term right here is going to go to 0, because it's C over x to the R. It's a constant divided by a power of x. And as x goes to infinity, that goes to 0. 1 stays 1, and this also goes to 0. So your answer is 2. So you have a horizontal asymptote at y equals 2. Let's see another. Let's do this one. Example 3. Okay. The limit as x approaches infinity of 2x plus 5 over 3x squared plus 1. When I have x approaching infinity, I need a strategy. And my strategy is I'm going to divide every term by the x to the highest power that's in the denominator. So you rewrite, and you divide every single term by x squared. And then you simplify. 2x over x squared is 2 over x. 5 over x squared doesn't change. 3x squared over x squared is 3, and 1 over x squared doesn't change. Now you're going to use that c over x to the r trick. So every c over x to the r is going to go to 0. You're left with 0 plus 0 divided by 3. So you have a horizontal asymptote at y equals 0. Excuse me. In pre-calculus, when we did this problem, we compared the n and the m. If n was less than m, we automatically had a horizontal asymptote at y equals 0. If n was equal to m, like we had earlier, we automatically had a horizontal asymptote of the leading coefficients. And if n was greater than m, there was no horizontal asymptote. All those rules are still true. We're just kind of backing them up with calculus. B part. The limit as x approaches infinity of 2x squared plus 5 over 3x squared plus 1. The highest degree of x in the denominator is x to the second. Well, the highest degree is 2, so we'll divide everything by x to the second. Again, how do we think to do this? It's just because I need a strategy for when x is approaching infinity. And this is it. And then I'm looking for all those c over x to the r's. But first, don't get ahead of myself. First, we want to simplify. So it's 2 plus 5 over x squared over 3 plus 1 over x squared. Now, every one of these constant over x to a powers goes to 0 when the limit approaches infinity. And you're left with 2/3. So you have a horizontal asymptote at y equals 2/3. Pre-calculus, let's look at it. My degrees are the same. N equals m. So my horizontal asymptote is the ratio of the leading coefficients. But yes, you have to go through and prove it with calculus, but you have a quick check for yourself. All right, last but not least, we have the limit as x approaches infinity, 2x to the third plus 5 over 3x squared plus 1. The highest degree of x in the denominator is 2, so we're going to divide everything by x squared. And then we're going to simplify. That's different. And then everything that's in the form of a constant or c divided by x to the r is going to go to 0. And you're left with 2 times infinity divided by 3. So we would call that infinity over 3. Now we know a limit fails to exist when it's unbounded. That's one of our first things from chapter 1. So this limit itself does not exist. Let's go and look at, so there is no horizontal asymptote. Let's let pre-calculus help us here. 3 is greater than 2, n is greater than m. So our rule, where did it go? If n was greater than m, there was no horizontal asymptote.